Where in the world are these scales that you stick buildings on to work out how heavy they are? I mean, that I find absolutely incredible. And so I thought, well, I want to go and see it, but then, so obviously I put it into Google Maps, and what did it say? Well, as you can see, the crucial point is this. It was 44 minutes away, so I was like, oh God, I've got to do this talk in an hour, so I probably can't get there in time, so what do? Well, I did that instead. I made the slides for the talk, and I sat downstairs and worked it out. So that's the interesting, the boring bit done while people were coming in and taking their seats. Why am I here? Well, I'm going to talk about quantum computing. There's some things that I'll try. And by the way, I apologize if the flow doesn't work so well. I've completely reordered all the slides because I didn't think it worked well the last time I did it. So why am I talking about quantum computing? Well, it's kind of a long story, which I'll try and keep short. What happened is last year, just coming up for a year ago, actually. In fact, just over a year ago, I was at Devox in Vienna. And this chap, very nice chap there, his name's Alistair Conniston, he did a talk on quantum computing. And I loved it, and I was really interested by it. I'd heard of quantum computing before, but I thought at the time, before I saw this talk, that it was still a theoretical thing that didn't really exist. Alistair talked about it, and after about 10 minutes of his talk, it went completely over my head. So I thought, oh God, I've got no idea what he's talking about. So I tried to talk to him afterwards, like there was a speaker's dinner, as there often is at these events, and he was pretty hard to talk to. So I thought to myself, well, I'm going to make a bit of fun of Alistair. So the following day was my talk, and this is me at Voxed Vienna. This is the video of me using that picture that you just saw to make fun of Alistair. And hey, I thought to myself, you know what? I can do a better job of explaining quantum computing to beginners. I didn't know anything about it at the time, but I still thought big-headedly that I could do that. So after that conference, a chap that was organizing that conference, Gregor's his name is, Gregor's Duda, said to me, can you please put a talk into Devox Poland? And because we'd like you to talk there. And I was like, okay. So I did my usual thing. At the time, I was talking about microservices in Vienna, so I put that talk in. And I just made this talk up called, Is Quantum Computing Really a Thing? And what you need to know about this slide is that the microservices talk was rejected because it's boring, nobody wants to hear about it. And the quantum computing talk was accepted. So I said to my colleagues at the time, who wants to learn about quantum computing? We've got 5 weeks to do it, which made me kind of feel like that. So what did I do? Well, I did a load of stuff. I learned a lot of stuff. I found out it was really hard. I'll do my best to explain it as best as I can to those in the room that have never heard of it. And ThoughtWorks then came to me and said, we need to have a strategy for quantum computers. So the global head of technology at ThoughtWorks asked me to do that, which I've been trying to do for the last sort of 9 months or so. One of my successes is this. I don't know if anybody's heard of the ThoughtWorks Tech Radar. If you haven't, the URL's there on the page. We have managed to get Q# into the Tech Radar. It's on the, I can't remember what we even call it, assess page, which means you should be looking at this stuff. So I'll show you a bit of Q# later. And recently, I've been invited to a thing by the UK government. Well, not by the UK government directly, that would be outrageous. But there's something called the Q Labs Innovation Project, which is going to start in London. They invited me to the steering group. And this is me at the University, UCL in London, the London Centre for Nanotechnology. That behind me is a quantum computer thing. Not quite sure exactly what it is. But this is a control thing. There you can see it's super cooled. And what I'll zoom in on is that it is 20.6 millikelvin inside that machine, apparently, which is, so I'm told, colder than outer space. We'll come to why that is important later. So, what exactly is quantum computing? Has anybody in this room programmed a quantum computer at all? No? Oh my. Normally there's at least one person that puts their hand up, and then I say to that person, you know what, you probably know more than me, so please come up to the stage and talk about it. On this occasion, perhaps I do know most out of everybody in the room. So let's talk about quantum computers and what we now call classical computers. Hey, who knew? We used to just call them computers, but now they're classical computers. So what's a classical bit? I hope everybody in the room is familiar with a bit. A bit is essentially a 0 or a 1. We use it for arithmetic. That there is a picture of, I'm told, is called a flip-flop circuit. It's an electrical circuit that represents either a 0 or 1, depending on the way the electricity goes through it. That's what classical computers use. Now, they take those zeros and ones, and they push them into logic gates. Logic gates can be OR, AND, NAND, various other things. And this here, this complicated-looking picture is, I can't remember, sorry, I can't see the picture very well from here. Yes, that is 16-bit floating-point arithmetic. And so what we're seeing there is all a classical computer does is it takes those basic logic gates, the ORs and the ANDs and so on, and sums them up into something that's useful. And then it puts those things together and makes them into more complicated stuff, which is more useful. But that is essentially all a computer can do. So let's introduce this term, qubit. So assuming we understand what a bit is, a quantum computer uses qubits. A qubit is a bit like a bit in the sense that every time you measure it, if you look at a qubit and say, are you 0 or are you 1, it will always tell you it's 0 or 1. It won't tell you anything else. However, they are, up until the point when you measure them, not only do they hold both a 0 and a 1 often, which is quite interesting, and we'll see why later, but also they hold what is called a quantum state, which means that they're somewhere in between 0 and 1, somehow. Doesn't really matter for this talk exactly what that means. If you really care about the maths, there's a link on one of the later slides that shows you what the maths is. But essentially, a qubit holds a value in 4-dimensional vector space. So if you remember your university maths, which I do, I studied maths at university, that means it holds a hell of a lot of information, way more than what a bit does. There are various things that can be used as qubits. It could be an electron, it could be an ion, it could be a subatomic particle, and here's one of the limitations of quantum computers. Nobody yet knows what the best way to represent a qubit is, the best way to use a qubit. Microsoft have something called Majorana topological qubits. They believe that that's the way forward. IBM is using ion trap technology, which, as I understand it, is an ion of something that is suspended between electromagnets. So the jury's out on that. And oh yeah, I've highlighted that bit in red. I should stand there so I see what the next slide is, but hey. A really cool thing about qubits is before you measure the value, they literally hold both values at once. So what that means is if you've got 4 qubits together and you perform a calculation on those 4 qubits, if you have them in a superposition state, you will make that calculation for every value from 0 to 7 at the same time. And that's really powerful. That's where the power of quantum computing comes from. Here's a picture. This is called the block sphere. I recommend, if you're interested, to follow those links I've put there. You can think of a qubit like that, as a point on the sphere. And when you measure the value, the probability of returning a 0 at the top there, or a 1 at the bottom, is kind of proportional to where the point on the sphere is at the time that you measure it. So you can think of it like that. It's a probability space. And the block sphere is a very useful representation of a single qubit. Now, just like classical computers, quantum computers have logic gates. They have an X gate, which rotates the pointer in that block sphere representation. Y and Z do the same, but in a different direction. You have a NOT gate that turns it downwards and so on. So they're very, very similar to classical computers in that sense. And IBM Q, those pictures there, I'm afraid that picture is very much out of date, and I'll show you in a moment why. One of the big things about quantum computing now is that nobody has yet built a language to understand how to aggregate these gates into anything resembling what we understand as arithmetic in classical computers. So if you want to program a quantum computer, you have to understand what these logic gates do. And I will show you what some of them do. So why would I care about quantum computing? What's the difference between quantum and classical? Well, as I kind of touched on, quantum computers at any given point hold exponentially more information than a classical computer. And they can compute things by definition, they can compute things in parallel, which is really cool. Unfortunately, at the moment, quantum computers aren't real. We still don't understand the physical hardware well enough to make them work, and they're hard to program. The simple fact is, unlike a classical computer that has all these abstractions built on top that we call operating systems and languages and so on, that doesn't yet exist in quantum computing. So you have to understand how to play around with logic gates and so on. So I'm now going to show you the IBM Q. This, I was very disturbed this morning. I was preparing this talk and just thought to myself, right, I'm going to check on IBM to make sure it hasn't changed since the last time I gave this talk. Yet again, it has changed. So, oh God. Every time I do a talk, I forget how to make... Are we seeing that? No, okay. I forget how to do the thing where my laptop can actually... here we go. I need to go to System Preferences, which I can't really do. Just talk amongst yourselves while I remember how a Mac works. This happens every time. I'm trying to... Oh, here we go. Are we seeing that? Fantastic. So, this is the IBM Q website. Today is the first time I've seen this. It evolves so fast. There are 2 5-qubit machines, as you can see. That means they're a quantum computer with 5 qubits in. There's a 14-qubit machine called Melbourne, which I've never seen before today, and a 20-qubit machine called Tokyo. If you go to this webpage here, you'll see that anybody can register an account. You can set yourself up as a quantum computer programmer, and you can play around for free. Now, if we look at the screen here, what we see is, up the top part here, this is called a quantum score, because it looks a bit like music notation because of the 5 horizontal lines. Each of the horizontal lines represents one of the qubits in their 5-qubit machine. And what you do is you can grab these things on the right here, and you can drop them there. So that's an X gate. What that does is, if you remember the block sphere representation of a qubit, it swivels it for 180 degrees for that particular qubit. There are 5 qubits here. They all start in the position of 0. But because I dropped that X gate on the first qubit, if I now observe the values of all 5 qubits, what I would expect to see is, and I can do that by clicking Simulate. It says, oh yeah, I need to, thank you very much. I need to measure stuff. So the pink things are measurement gates. So I'm going to drop those on and measure the value of all 5 qubits. And if I click Simulate, what that does is it doesn't submit it to a real quantum computer. It submits it to a classical computer that's simulating the quantum behavior. So, apparently I have to give it. It's been a bit slow, but there you go. So what we see there is, as we expect, 100% of the time, what the simulator does is it runs the simulation, I think 100 times, perhaps 1,000 times, I'm not sure. And it tells you the results. So in this case, what we're seeing is 100% of the time, 1 was the value of the first qubit, and 0 was the value for the other 4 qubits. OK. So if we go back, for example, drop an X gate on, I don't know, let's say the third one, and simulate, what we should see is 00101. Sorry, 00101. And that's pretty much as we expect. Hello. So that's so far not very interesting. I think we'll all agree. So let's make it slightly more interesting. Now, if I, instead of putting an X gate there, there's a delete button somewhere, I think. Oh, there it is. Instead of putting an X on that, I'm going to drop this guy. And this is the most complex gate that I'm going to talk about. This is called the Hadamard Gate H. What the Hadamard Gate does is if you remember that representation of the qubit, the block sphere, it rotates it through 90 degrees, so that it's pointing exactly halfway between the 0 at the top and the 1 at the bottom. So when you measure the value of that qubit now, 50% of the time or so, you should get a 0, and 50% of the time you should get a 1, which sounds nothing more than a random number generator. But remember, the power of that now means that that qubit, if it's involved in a calculation, will use both values. So the quantum computer, for every qubit that isn't either pointing straight up or pointing straight down, both values will be used in the calculation. So the question was, do we have to separate the results? We'll come back to that, because it's a very good question. I'll show you what happens now. When we run this on the simulator, what we should see is that, there we go. About half the time we get a 0, and about half the time we get a 1. So in this case, 44% and 56%. If we run it again, we'll see something slightly different. What have we got there? 45%, 55%. OK. Is anybody in this room familiar with Schrodinger's cat? I was hoping to see more hands then. So I told my daughter the story of Schrodinger's cat some time ago, and she said to me, "Daddy, why would anybody do that to their cat?" I was like, well, no, Clementine. He didn't actually do it to his cat. It was designed to be a story about how absurd the Copenhagen interpretation of quantum mechanics was. So it's a very popular thing to do in quantum computing to simulate Schrodinger's cat. Now, if we look here, this is a quantum circuit that simulates Schrodinger's cat. The fourth line down has a Hadamard gate on it. That represents the piece of radioactive material. The idea with Schrodinger's cat is, after a certain amount of time, there's a 50% chance that radioactive decay has occurred, and there's a 50% chance it hasn't. So the Hadamard gate is perfect for putting that into that state. So it has both the radioactive occurred state and the radioactive decay didn't occur state. The next thing you see is that little plus sign thing next to that. What that is a CNOT gate. If you know about classical computing gates, you know about a NOT gate. So a CNOT gate basically says there's a control bit, which is the lower bit. If that bit has the value 1, it flips the value of the other bit. If it has the value 0, it does nothing to the other bit. So what we've got there is the fourth qubit represents the radioactive decay. The third qubit represents the hammer. The second qubit represents the vial of poison inside the box with the cat. And the fourth qubit represents whether the cat's alive or not. I apologize to the cat lovers in the room. So in each case, what happens is, if the fourth qubit has the value 1, i.e. the radioactive decay occurred, then everything else happens. And you can see that they're linked by that CNOT gate. OK? Now, the reason why this is important in quantum computing is that the CNOT gate leaves a relationship between the two qubits, which is what Einstein called the spooky action at a distance. I don't want to go into that in too much detail. But that's called, can't remember the phrase, excuse me. So let's run this circuit. What we've got here, you can see I've run the programs on several times in history. Hang on a moment, how do I do this? Let's go down to, here we are. Because I happen to know that if I go to, I think it's this one, here's where I ran the circuit the first time. And what we'll see is that, as you'd expect, either everything is true or everything is false. And that's an illustration of entanglement. That was the word I couldn't bring to mind a moment earlier, between the qubits. They all have to be true or they all have to be false. That's obvious from the circuit, I hope. Now, the slightly interesting part of this is that bit there that I just showed you, that was a simulation. I executed that circuit against a simulator. If we come to this execution here that I've highlighted, that I actually submitted to IBM's real quantum computer, and I got the real quantum computer to execute it to see what I got. Anybody can do this. Just set up an account. You have a certain number of credits. It costs credits to run your program against that quantum computer. So I don't do it often. But I do sometimes phone the guy up at IBM and say, hey, can you give me all my credits back? Which he does. So let's have a look at the results from when I ran it against the real quantum computer. Now, as you can see, it's not so obviously one or the other. What we're seeing is that what the real quantum computer said was 37.1% of the time the cat was alive. 29.4% of the time the cat died. And there are 14 other outcomes in the middle. Which kind of mean actually, no, not kind of mean, they actually mean nothing. And this is what we're seeing here is an illustration of why quantum computers are not ready yet for the mainstream. What we're seeing is that that perfect picture I showed of the block sphere earlier, it's kind of not possible to do that yet. So there's something called quantum decoherence, which you can look up, and every qubit, it only has a very, very limited lifetime, and we're talking about milliseconds before it's useless. And every time you push it through a logic gate, one of the quantum gates, it leaks information into the gate, and the gate leaks information into it. That's something that just simply doesn't happen in classical computing. And what that means is you have a very, at the moment, a minuscule lifetime for the quality of your quantum computer to work with. And that's the biggest limitation to quantum computing as it stands. And that's also why things have to be supercooled, because heat will destroy the quantum information, the quantum state. So that's why I was standing with that ridiculous grin on my face in front of that supercooler thing in London a couple of weeks ago, because hey, I've never seen a supercooler that's colder than space, but hey. Right. So that's IBM Q. By all means, set yourself up an account, go back to it, and have a look at it. And one day I'll work out how to get back to my presentation without having to needlessly fill the time with stuff like this. I think, excuse me while I get my glasses. That one. Okay, so I think we just spoke about IBM and everything. There's a picture of how you get to the designer thing. So where is quantum computing now? Ah, wow, that's not showing on my screen. How do I get rid of that? Oh, it's gone. Right, if I press that now, will it come back? Ah! Gone, thank you. Right, where is quantum computing now? Okay, so everybody loves a Dilbert cartoon. This is kind of where quantum computing is. Does it exist? Yes. Can we program quantum computers? Yes. Can we submit those programs to real quantum computers? Well, kind of. We can use the IBM Q machine. If you've got enough money, you can pay to go on a bigger machine. You can go to Rigetti and so on. So we've spoken about IBM Q. I showed you IBM Q. Microsoft believes they will have working quantum computers within 5 years, and this article was written back in March of last year, so I guess that means within 4 years now. But who knows? I still haven't seen anything publicly. I've spoken to the people at Microsoft about 6 months ago. They're kind of regretting this press release, I'm told, but hey. But what Microsoft does have, and I'll show you shortly, is a quantum development kit. Q# is a new language that Microsoft wrote that enables us to program quantum programs and execute them against the simulator, which any computer can host, and I'll show you all that shortly. There's a company called Rigetti in America, which is building real quantum computers. They have announced that I believe something to do with publicity, something called the Quantum Advantage Prize. For anybody that can come up with an algorithm that is a real-world problem that can be solved better in a quantum computer than it can be in a classical computer. And there's $1 million prize available for it. My suspicion is that they themselves expect to get there first because of all their work, but they've announced this prize just to give themselves publicity. Okay. Last October, I saw a talk in London by a couple of consultants about quantum computing being used in the financial industry. So that's happening. We're now, and I'm talking to this company about how ThoughtWorks can get involved in helping with that, because the point is we can write the programs, but we don't yet have the computers to execute on them. And this, I think I'm in that picture. God, it's a terrible photo, I apologize, but recently the UK government has announced something in the hundreds of millions of funding, and there's this group being set up in London called the Q Labs Innovation Project, and weirdly they invited me to be on the steering committee to represent ThoughtWorks, and what we're trying to do is get people together from industry and from science to understand how to make real applications out of quantum computing. So, what's required to make a real quantum computer? Well, that's got pictures on my computer. Got colors even. Oh, no, it hasn't. Oh. So, you need qubits. I mentioned that the qubits are very short-lived, and they decay, and they have all this noise going on. That's really hard. That's a physical problem that they're trying to solve in amongst other places at the London Centre of Nanotechnology, which was that picture earlier. You need to have an interface between the qubit thing, which, remember I mentioned that the most common technology that I understand is that it's an ion suspended between electromagnets. So you need a way of giving that information, of changing its state. My current understanding from what I was told by the people at UCL is that what they do is they fire microwave beams at it, and that changes the state, and that alters the state slightly. But you can imagine that that's kind of difficult to do. So that's really hard. And you need error correction. You remember the slide earlier with all the pictures of the proper state 0 and the proper state 1 and the 14 states in between? So because we know that qubits are inherently full of errors, there needs to be some method of correcting those errors. That's a really hard problem. There are whole talks in more complex context than this about how to do that. And believe me, I don't understand it. You need cryogenic systems. You need, as I say, to supercool the stuff. Well, that's a solved problem, but it's expensive. So we're not going to have these things in our front room anytime soon. You need integration with a cloud provider, yeah? Because the idea is what's going to happen, Microsoft are talking about it, Amazon's talking about it, there will be a quantum computer in the cloud and you'll buy time on it. Essentially like what's happening with the IBM Q right now. So that's going to happen. As soon as it's a real thing, Amazon will make it happen or Microsoft will make it happen. So I don't think we need to worry about that. And finally, the algorithms and the applications. Well, interestingly, this is already happening, as I say. Because we have Q#, because we have QIS kit from IBM, there's a Python-type programming language, we can already write quantum programs. And you know what? It's really good fun, because I've done it. So, what is the point of a quantum computer? So far, I've shown you a little bit of randomness. I've shown you that entanglement works. What's that going to actually mean? So what's really exciting is complex dynamical systems. Because of the fact that a quantum computer can compute all of the possibilities at the same time and get to some result, what that means is we can use them to do predictions. We can use them in things like what this picture is. It's from D-Wave, as you see. This is a representation of the traffic flow in Shanghai, I think, or perhaps Beijing. I can't remember which. And they're using a quantum computer to predict where the traffic will be. It's far too complex for me to explain right now, but it's happening. Another thing that's interesting is that IBM, again, it's a complex dynamical system. IBM bought a weather forecasting company 2 years ago. An IBM person told me that the reason it seemed an odd thing for IBM to do, somebody from IBM told me the reason why they bought that company was because they wanted a real-world thing to test their quantum computers on. So essentially, what they're doing with the quantum computers is they're using the power to parallelize those computations to run simulations over and over and come out with what might be the most likely result, which is what you do in weather forecasting. So I'm going to kind of demonstrate that. That's my daughter Clementine, who was 12 yesterday. Sitting there, you can see that funny black thing. That's Clementine's cat. We mentioned Schrodinger's cat earlier. Well, that's Clementine's cat. Why do we care about Clementine's cat? Well, as I said earlier, you remember I mentioned Schrodinger's cat, and my daughter said, well, why on earth would somebody do that to their cat, Daddy? Well, of course they didn't. Oh, sorry, I forgot that was there. That's my other daughter, just nicking one of my shirts. Here's Clementine's cat. She is showing the standard cat mood, which is, of course, anybody that owns a cat knows is utter indifference to human beings. So what I tried to do when I was in Vienna last year was to run an experiment on the cat to see if I could actually impose a superposition of moods on the cat. And what I found was I could actually do that. I could impose 8 different moods on the cat at the same time. All of which leads me to a quick demonstration of what it means, the 2 different... here we go. Can we see that? Oh, God, this is working better than it's ever worked before. Oh, no, until I do that. Oh, my God, that worked. Can everybody read that? Shall I make the text bigger? Does Command plus work in here? Oh, my God, it does. Right. What we have here is Q#. If you download, I think I've got it on a slide in a couple of minutes, the Microsoft Quantum Developers Kit, you can get all this stuff. They invented a brand new language called Q#, which is purely for programming quantum computers. The way it works is it has to have a classical program, which in this case is called driver.cs, because that's the default, and I never bother changing it. And what that does is it runs the quantum program. So the idea is what we're doing here is we're literally simulating what will happen in the real world when you have a real quantum computer. So you can see in here there's a main method. Oh, by the way, this is a Java conference, isn't it? Sorry. It's C#, but if you look at it and close your eyes half shut, it looks the same. So what it does is you can see it creates a quantum simulator object there, instantiating it, and then down here it runs a thing called cat mood experiment, which is the quantum algorithm, and it tells it what quantum computer to run that on. So it's using the simulator that I created earlier. So the idea with all this is, of course, that when there is a real quantum computer in the cloud, instead of using that simulator, you'll run your same code, but you'll pass it the real quantum computer. You'll pass it some instance, some pointer to the real quantum computer. So what does the quantum code look like? Well, as with all demonstrations, it's pretty trivial. So I'm going to show you here. I don't know if anybody's used F#. I've never had. I'm told it looks a bit like F#. Maybe it does, maybe it doesn't. What we've got here is an operation called measure cat mood, which returns basically 4 things, 4 results. And here what happens is it creates 4 qubits. Now, these qubits represent the members of my family. So the first qubit in the collection represents me, The second one represents my wife. The third one, my daughter Clementine. The fourth one, my daughter Felicity. What happens every day when the cat gets hungry is she comes to me and she asks to be fed. And she does that in various ways, which anybody who has a cat will know about. If I feed her, she eats the food and then immediately forgets I fed her, and then goes and asks my wife to feed her. Again, if my wife feeds her, she immediately forgets she's been fed and moves on to Clementine and then Felicity. So she's perfectly happy as long as she gets fed more than once. That's the way she works. So what the code is doing here, by the way, this is available on my GitHub. There's a slide with the link on it later. It applies the Hadamard transform to each of the 4 qubits. What that means is it puts every human into a state where they both might feed her and might not feed her, with about a 50% chance of feeding the cat. And then, I told you this was a trivial program. Later on, here we're asserting things just to check that the program didn't break. And down here, we basically measure the value of each of the qubits and then send it back to the C# program, which is out here. And what we see is, I'm just going to comment out this lower bit because we'll come back to that. What it does, and this is simulating the idea of, what I've got here is a really trivial example of the weather forecast type thing. In the weather forecast, you run the same simulation thousands or tens of thousands of times and work out what the most likely thing is. So in this case, what I'm doing is I'm submitting this program within the cat mood experiment that we just saw. I'm running it 100 times and then examining the results. Oh my, Visual Studio wants to apply the latest update. I think I'll go for later because I don't think everybody wants to see that happen, do they? Thankfully, I don't use a PC. What happened, I've seen somebody with a PC and it whacked an auto update in during her talk and she had to go, oh my God, and borrow a computer from someone in the front room. So, I'm going to build the program. I hope it works. Yay, build successful. So now if I run the program there, we should see some outputs. And it will just basically tell us how many times the cat was happy and how many times the cat was sad. So nothing mega about that, but I'm just illustrating the fact that that's a really... Oh, not only did I type the wrong thing, but if I run it again, we should see a slightly different result. It's to do with the binomial... Oh, that's never happened before. There you go. Just to show that I wasn't lying. And hopefully we'll get a third different result now. So this is brilliant. I love the fact that everybody's laughing. They think that it's part of the show. That has literally never happened before. If this says 7228, I'm going to leave the room. Ah. So there you have a fairly simple program that illustrates that you submit stuff to the quantum computer, you measure how many times it does this or that. I'm going to show you my second illustration now. If I go back to the Q# program, and again, it's pretty much it's a similar thing. It's the same scenario. The cat now, where is it? Here it is. This one, who fed the cat? What this program does is essentially the same thing. It puts 4 qubits into superposition and it measures whether I fed her, whether my wife fed her, and so on. But instead of doing it 100 times, it just does it once and it sends the value back out. And in the C# program, what we see here is that the C# program is now doing the iteration. So what it's doing is it's passing the stuff into the quantum program. It's waiting for the result. It comes back out. And what this is modeling, which is something I'll talk about in a moment, is a bit like an optimization problem, where you put in a massive multivariate problem, you give it loads of stuff, you see what the answer is, you adjust your input slightly and put it in again. So you keep going backwards and forwards. That's the other big use case for quantum programming. And if we just run this program, what we'll see is that what it will now do is it will run the program 100 times, I think. And each time it'll output either the cat being happy or the cat being sad. Have to build it again, you know, because I changed it. So let's see what happens. We should see it going down in the output window one by one. So you see we get some sad outcomes and some happy outcomes. Okay, so those are the two different ways that we can use quantum computers. I completely haven't mentioned quantum annealing because I don't understand it. But if you want to look that up, please do so. Well, all I'm talking about is gate-based computing. Right. Going to go back to my presentation, I hope. Is it working? That's enough code now. I hate doing code live on stage. It always goes wrong somehow. Right, I've got that stupid thing there. Let's get, well, last time I did nothing, so I'm hoping it'll just go. If I just stand here like this. What do I have to do? Ah, there you go. This is Francis Lacan from IBM talking about financial applications. This happened in London. If you want to see a video, go to that URL there. A really exciting thing about quantum computing is organic chemistry. Using that technique that I said about putting in some values, waiting to see what the result is, and putting them back in and so on, there's something called a Hamiltonian function, which the mathematicians in this room have probably heard of. A Hamiltonian function defines the energy of a system. Organic chemistry, in fact, any molecules, always tend to the lowest energy state that they can. And that defines the chemical properties. That molecule there is caffeine, which I'm sure you've heard of. We understand caffeine very well, but it's the most complex molecule we understand. That molecule there, or it's not even a whole molecule, it's part of a molecule, is called iron molybdenum complex. I can't remember the exact name. If we understand that, it's massive. Oh, I don't remember doing that slide, but hey. This is why we should care. At the moment, 3 to 5% of the entire world's production of natural gas that we get out of the ground, out of the sea, out of fracking, whatever, goes into this process here. This is the Haber-Bosch process. The Haber-Bosch process makes ammonia that we use for fertilizer. So almost 5% or whatever of all the world's natural gas is used to make ammonia. Beans, if you remember your school days, are used in something called crop rotation. Bean plants use that iron molybdenum complex on the previous slide to make ammonia from atmospheric nitrogen. And they do that with zero energy uptake, as far as we can tell. We have got no idea how that works. But it is the promise of quantum computing that we will start to understand how those organic chemicals work. So potentially, we might not have to do what we currently do with the world's natural gas to make ammonia. Now, what I'm going to finish with is this. It is the elephant in the quantum room. I don't know if anybody else in this room is from the UK, probably not. If you're not, you won't have a clue what that slide is showing, but there you go. Anybody know who these three gentlemen are? Hands up? Yes? No? No hands up. I'm glad about that. If you put your hand up, I'd call you a liar. They are James Ellis, Clifford Cox, and Malcolm Williamson. We will come back to those men. Does anybody want to hazard a guess about who these two gentlemen are? They are Diffie and Hellman. You've probably heard of Diffie and Hellman. Now, in the context of that previous slide, does anybody want to make a guess at these three gentlemen? They are, I think you're saying the same that I'm saying. They are Rivest, Shamir, and Edelman. They are the people that came up with RSA. Why do we care about RSA? Well, public key cryptography. We all rely on it. What is it? Essentially, it relies on the fact that it's easy to multiply two numbers together, but it's hard to understand how to reverse that operation. All public key cryptography works on that. All cryptography works on that assumption. Factorization takes a long time. It's impossible, effectively, on classical computers. If you build a computer that uses every electron in the universe as a bit, such a computer will take longer than the lifetime of the universe to factorize a 3072-bit RSA key, so I'm told. Shor's algorithm. Has anybody heard of Shor? This is why I'm not going to go through all these steps, but essentially, Shor's algorithm is for factorizing large numbers. That's it laid out, bare. What does it mean? Well, the first bit is a bit of number theory, if you remember from university. We don't have time to do this, but I'll show you pictorially now. I'll come back to the quantum period finding routine in a moment. I had to work out how to program Shor's algorithm into a computer a while ago. So what did I do? I went onto the interweb, as one does, and I made a spreadsheet. And what we can see there is some of the spreadsheet here. What we've got there is successive powers of 4. So 4 squared is 16, 4 cubed is 64, and so on and so on and so on. The idea is you keep doing that, but modulo the number you're trying to factorize. So I was trying to factorize this number, 1,517, which you kind of can see there, but it's a bit small. And if we scroll down and scroll down and scroll down, so each time the number gets bigger than 1,517, you take off 1,517 till it goes to a number lower. And what we see is 4 to the power 90 ends up being 1. So it repeats. The cycle repeats after 90 times. And if you think about it, because we're using modular arithmetic, the cycle must repeat at most 1,517 times. Because there's only 1,517 different results that you can get. So what I needed was, and as you can see, I did it for various different numbers. We don't need to see the actual results here. I don't know if I scroll down, we'll see it eventually. God, whatever that number is. 15, oh, there it is. 15 has a period of 549. Eventually I found this number, which is 9 mod 15, and found out that its period was, or is it 14? No, this is the slide I want. Its period is 28, and crucially, I discovered that its period is 24. The half period is 12, which is a number that doesn't overflow in Google Sheets. So therefore, I could use that number to work out what the factors are, which happens on the next slide. Yep. Oh, God. Thank you, Stefan, but they made me start late. Yeah, okay. So, there's the workings of Shor's algorithm. Do I have to do that to get rid of that thing? Yay. Here it is. Here's the real numbers, if you're interested. Some big numbers. Lo and behold, there we go, 37 times 41. What does this mean? Well, Shor's algorithm, the crucial point is when I simulated it myself, it took forever. However, step 4, which is, here's my colleague Andrew. He wrote some quantum code, which is available on his GitHub there. And it ties in with the quantum code that's in my GitHub, which is on a later slide. We managed to factorize numbers using Shor's algorithm. Not big numbers, but Shor's algorithm runs in polynomial time. What does that mean? What that means is that very soon, when we have real quantum computers that are big enough, that have enough qubits, all of your RSA encryption is worthless. As you can see, it's quite a long way off. Well, we'll see. So, we're a long way from that. In order to use Shor's algorithm effectively, you need to have 3 times as many qubits as the length of the key. So for a 1024-bit key, you need about 3,000 qubits. The biggest publicly known quantum computer at the moment is about 72 qubits. So what do we do if RSA encryption dies? Well, there is something called BB84, which is 100% secure. It's quantum key distribution. That will work. There are classical algorithms, some of which I list here, lattice-based, supersingular, symmetric key. All of those will be quantum safe. And there is an open source project that's talking about quantum safe stuff. So how long will it take for quantum computers to be ready to break your RSA? Well, a few years. But, and there's something about quantum key distribution. Here's how much money is known to have been spent on quantum computers in 2015. This does not include government spending, and it does not include all the secret services around the world. That's already a lot of money. Now, let's go back to my history lesson from earlier. Diffie and Hellman published their paper in 1976. Rivest, Shor, Edelman, they published their paper in 1977. Do you remember those three gentlemen at the start that nobody's heard of? Well, who are they? They work for British Secret Services. The British Secret Service had RSA and had Diffie-Hellman long before they were published. What does that tell you about the spending that is currently going on in the Secret Services on our RSA encryption? And moreover, and this is the thing that I want to leave you with, all of your RSA traffic is currently being collected and harvested. It will still be decryptable 5 years from now or 10 years from now when those computers exist. So we need to be thinking about that right now. And that's what I'll leave you with. Thank you very much for listening. I'll take questions in the bar.